you do in one day? When it comes to how you spend your time, you want it to be intentional, impactful, inspiring, and you want your investment to be worth it. The Modern Lab Leader Online Symposium is your chance to unplug, refocus, and level up your leadership in just one day. Learn from world-class speakers and thought leaders across industries. Gain practical tools to amplify your influence and lead with confidence. Invest in yourself. Invest in your future. Register today for free.
Hi, I'm Heather James, Conference Producer for Technology Networks, and I'm here to introduce our next talk, Applications of NIRS and NIR Imaging in Food. I'm pleased to welcome our final speaker, Dr. Vincent Baeten. Dr. Baeten has over 25 years of experience in European projects dealing with the development of spectroscopic methods. He has participated in several European projects dealing with the quality, safety, traceability, and authentication of food and feed products. He's been awarded many accolades, including the 2011 Q Interline Sampling Award for the outstanding contribution in sampling applied to spectroscopy methods, and the Thomas Hirschfield Award for his outstanding achievements in near-infrared spectroscopy. He currently works as the Scientific Director at CRAW, Walloon Agricultural Research Centre, and is the Head of Quality and Authentication of Products Unit. A warm welcome to you, Vincent. Following the presentation, we will have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And without further ado, I will now hand over to Vincent to begin his presentation.
Good morning, everyone. Thank a lot for the introduction, and I'm glad to be here with you online, but that's great also in order to give you a small introduction of what we can do with vibrational spectroscopy, and more exactly with infrared, near-infrared spectroscopy and near-infrared spectroscopic imaging. So my name is Vincent Baeten. I'm working at the Walloon Agricultural Research Centre. The Walloon Agricultural Research Centre, it's a European research centre of medium size, we would say. We are about 420 people, 120 researchers working on agronomic science, and we have different trial fields. We have also orchard, greenhouse, and different farms, but also laboratories. In fact, as you know, if you want to understand something, if you want to change something, you want to improve something, you need to make measure. And so our center is quite strong in the development of different analytical methods. And in 2020, we decided to rescape a little bit our institute, and we built a new unit called Quality and Authentication of Products. I'm managing this unit, and it is a unit about 34 people, and we work in the development of a sustainable method in order to reinforce and assess the quality and authentication of agricultural and agro-food products. In fact, this team, it's about 7 research team together, and each one is focused on different analytical technique. And so, for instance, we work on the molecular biology team. They work on the detection of GMO and species identification with PCR technique. We have also a microbiology lab where we are working on the development of ferment and other aspects about development of about consortium. And also we have a microscopic lab where we look, for instance, for the detection and quantification when it is possible of adulterant, but also about contaminant and impurities. And finally, we have also another lab where we work with mass spectrometry for the authentication of animal food product. But I say this is the 4 labs that I will not speak today. I will focus on 3 of them. This is the lab where we are using vibrational spectroscopy. And as you will see, we have quite a long experience in the use of vibrational spectroscopy to tackle some challenge in food analysis. And here you have a short summary, I would say, of the 3 labs. So the first lab, the historic lab, is managed by Audrey Pissard, and it is with the use of near-infrared spectroscopy as benchtop instrument, and they analyze on the year basis about more than 30,000 samples in order to determine the different characteristics we can determine with such a technique. With the year, we have developed a second lab where we are working more with Raman spectroscopy, mid-infrared, and also imaging spectroscopy. This is something I will elaborate a little bit more in the talk. You will see that there is a definitely advantage in the food analysis by imaging. But also in this lab, what we have, the responsible of this lab is Juan Antonio Fernandez Pierna, and is really an expert in chemometrics, and so he's managing also for all the unit. He tried to help for the data treatment. That is a key issue today, more and more. And so this is there also where there is our team of chemointuition. And the third lab about vibrational spectroscopy, it's more recent. We just launched this lab a few years ago, and the head of this lab is Philip Vermeulen. And the purpose is to bring our vibrational spectroscopic technique to the field. I will just present you very shortly some issue we are trying to tackle. And there we are really in the lab to the sample approach. It means that we go with the lab to the samples. That's changed a little bit our mind. And we do that, we create a specific unit for that because we believe that vibrational spectroscopy is really maybe one of the best technique to do analysis online, on field, in the orchard, in the greenhouse, and so on. So there is a common issue about these 3 different vibrational spectroscopic labs. They all use light, in fact. And we try to use light in order to understand what's happened in the product. So, you know, this is here, we are in the visible range, not in the infrared range, but it's exactly what we do. When we see a green leaf, we know that if the leaf is green, it is because there is interaction between the light coming from the sun and the leaf and the composition of this one. And what we can observe in my country, in Belgium, it's fantastic, but also in all other countries where the autumn is present, we can observe the change during the autumn when the composition of the leaf are changing and then the color are changing, and that makes life very fantastic. What we do with infrared spectroscopy, we are doing something very similar, but we are just playing with another other radiation. You know, the visible part, the visible region, it's only a very small part of the electromagnetic spectrum. You have here a slide showing you the electromagnetic spectrum, where we can see that if we express in the frequency domain, that the visible is a very small one. We are between 380 nanometer up to 780 nanometer. That's not so wide, it's very reduced. But what we can see is we go to the right side, let's say, I would say to frequency, to higher, lower frequency, sorry. We have there the infrared region, where we have the near infrared, the mid infrared, and the far infrared. That is what we explain in food. If you go to other kind of analysis when with satellite, and they use also infrared, they would speak more with the terminology of near infrared and SWIR, but we are there, and then the infrared region corresponding to our mid infrared. But there we have a lot of technique existing today to make the analysis of food product. But you know, there is also the microwave. If we go to the right side of the slide here. And there what we can see is that we have a technique also that maybe you know that we use in the food to dry, but also to determine other important parameter. Then we have the radio wave, and there we have, for instance, resonance magnetic nuclear, NMR, technique. And if we go now to the left, we have a UV technique there where we can use to make interrogation of the food product, and also X-ray. This is something that is used quite a lot when you want to detect a foreign body presence in the product. It's quite interesting to go to that. But today I will speak about near-infrared. So it means for me, I'm food scientist, so it means the wavelength between 800 nanometer to 2500 nanometer. And this is something not new in our institute. Our institute started to work with such a technique in '79. So you can imagine that we have quite a long experience, and we have worked during years, of course, with near-infrared spectroscopy with benchtop instrument. Then we went also with the instrument to the harvester, then to the online. So we have used a different kind. We are using different kind of instrument, also coupled with fiber optic that allow you to go to measure at different point. And with the time, we have also started to work with mid-infrared. You know, mid-infrared, I will come back to that. It's quite used a lot in the analysis of milk, but also later on, we start with imaging in 2001, where we buy the first imaging system to apply to food. It was quite new at that time. Now I would say it's more common. And then in 2007, we start also to work on Raman spectroscopy. I will not discuss this today because the time is not enough, but it's also a very exciting world. But what is booming, I would say, imaging, this is since 2 decades, but since 1 decade, certainly, in the near-infrared spectroscopy, it's handheld device also. It means that we go to smaller and smaller spectrometer. Very interesting because we can go to the sample. The price go down, quite cheap, but of course there is we reduce the range of application, and this is all the family of the baby NIR we call. In total, in our institute, we have more than 35 instruments of different kind, and one of our specialties is to develop model. To that, I will come back to that. To develop model, but also to transfer the database or the model from one instrument to another instrument. But okay, maybe for the one who is not familiar with spectroscopy, how it works. So we try to catch the interaction between the near-infrared light and the product, okay? And for that, we use a spectrometer. And here you have one of the instruments, it's a benchtop instrument. And you can see here, you have cups where you have the sample, and you can fill up different kind of cup, and then you present the cup to the instrument, and it will measure from the bottom of the cell, and then in few minutes you can get the spectra, and you have an example at the bottom of spectra we get. In this case, the instrument select here, the benchtop, give the full information in the visible range and in the near-infrared. And you can see the kind of information we have. So we get this in benchtop instrument in a few minutes, I would say. I can tell you that online we can get it in a few milliseconds if we wish. Of course, there is a cost in terms of signal to noise, but we can be very fast in terms of acquisition of the information if we go to different kind of technology. This one, it's a dispersive instrument. It's more slower than a FT instrument, and an FT instrument you can get in few seconds very good spectra also. So this is the information we get, and here, just to telling you, it's a 3 different spectra from 3 different extracts we have done from wheat, okay? And you see that we have the absorbance for not all, but most of the near-infrared region, and also we have the wavelength from 1100 to 2500, and we have this expressed in absorbance. It is a logarithm scale. Here you have the oil. You can see the specific band. I put here the wavelength. Then we have here the specific fraction, the gluten. Okay, it's the major fraction of protein from wheat flour, and you can see that we have other specific band. And here, for instance, this is the starch. Okay, and so this is with the kind of information we'll play. Just to telling you that in fact one band corresponds to a vibration. So what's happened when there is interaction between the light and the matter, we have a molecule vibration, and this make that the wavelength will be absorbed or not by the product, and this gives us information. What is very, very interesting with such kind of technique is that the same technique can be applied in different products. I will come back a little later on this, but also what is interesting is that we can apply this in the laboratory, as it's explained here, as offline. So this is when you take the sample and you go to the laboratory to make the analysis. In blue, you have the flux of samples, and in red, you have the flux of data. But what we can do, we can work at line. So we can put the instrument just near the line of production, for instance. We can put it online or inline. So this is what we try. This is our goal sometimes for, I would say, the big company. They want to have inline. It means that they have a sensor based on vibrational spectroscopy that will give us signals to the automation in order to adapt the process. This is what we do. And so there is a lot of expertise you need when you want to do that, because spectroscopy, what they deliver, spectrometer, what they deliver, it's absorbent regarding wavelength. And so we need to be able to calibrate. And here you have different expertise that we have developed with the time. It's transfer of data, standardization, all about sample presentation. It's simple spectroscopy, but it's very important the way you present the samples, because you can make a big mistake there and then not have what you want. There is also a lot of study that we have to do in order to work with such a technique in ISO 70025, which succeed. It's not too complicated at the end to do that. And we organize also for network different interlaboratory study, training, chemometric courses, and so on. So this is one thing in our institute. We are quite lucky because we work with a lot of different products, and we work with our colleagues from the different unit. Here you have the name of colleagues from other units but specialize in the topic, and we work with them on the different product with spectroscopic technique. And that's very nice because they know very well the technique, but they are specialized in the product we analyze. This I will skip because it's just to give you a signal that's not always easy when you have the information, when you have the spectra, and then to go up to an answer, analytical answer. Let's say that you have the spectra of wheat flour, and then you want to determine the protein. You have to build models, and there is different step. And this is not something difficult, but you have to be very strict and to be very careful. You have to explore the data and to check what you are doing in order to avoid any overfitting. When I speak about the development of model, we are not focused only on targeted analysis. Targeted analysis, you say, I want to determine protein content. Or if you are in the case of detection of fraud, I want to detect the presence of melamine or of whatever, adulterant and so on. That's targeted analysis. But more and more, the interest for the laboratories and the industry is to have untargeted technique, to check if the sample they have, the raw material, it's okay or not. If the sample process, it's okay or not. Just to be able to flag and to say, okay, these samples, there's something that I don't know what's happened, but there is something I have to check to be sure that I get what I expect, or I sell what I promise to sell. And this is all about untargeted detection, where in fact, what we want to do is to detect any problem that can come from any sources before it came, let's say, an economic problem. So if when you have raw material, you can check and say, okay, stop, this raw material do not correspond to what I expect. It's better that to wait to produce. And if you have to wait laboratory results, sometimes you have to wait a few days. And so it means that it will be a high cost also to be late in order to get the information. And so vibrational spectroscopy, near-infrared spectroscopy are really technique for untargeted detection also. That's quite interesting. And untargeted detection is very important in the fraud. You know that there is in food more and more concern about different problem in terms of mislabeling, of adulteration, of different problem. And so we have to be able to check more a portion of the sample, not only to check in the lab, but also to check in the factories, in the retailers, and so on. And so this is something that we are doing since years in our institute. But just to demystify, when we speak about construction of model, and that's what we speak in our language, is that we have the spectra, so we have the database. So this is algebra a matrix, okay? And then we will have at the same time also the reference value. The reference value could be only the observation. This is a good or bad sample. This is an adulterated or non-adulterated samples. And but also could be the protein content and so on. And then with both information there, what we will do, we will build a mathematical model. It's what now we call machine learning. And this part, it is in the machine learning. When we have a model, what's nice, we can get a new spectra from a new sample, and then we can apply the model and have a predicted value. And this is what we are doing daily. This is what is done in the food industry daily also. If you look to the milk, for instance, for the milk analysis, most of the analysis is done by mid-infrared. Okay, so it's in Belgium, it's thousands of samples analyzed. And so this is one of very, very important application. If you look to the feed, it will be near-infrared spectroscopy used to determine different parameters and so on. So this is a technique highly yet used in the food industry and also in the laboratory and official control laboratory also. What is very interesting there is that when you have developed a model, you have the possibility that this model or this database, you have two strategies that you can be used by a network of instruments. And here I present just a small network we have in the south of Belgium. We start this network in 1989 and it's still running, where we have 9 laboratories plus 1 in Luxembourg, where we have the same instrument, the near-infrared, and we share the database. And what is our role in the Walloon Agricultural Research Centre is to assess that the network works perfectly and that all the instruments speak the same language. And how we do that? We standardize the instrument. And doing that, we are able to check that all is okay. And we can, for instance, here you have the results of prediction. We can adjust the model in order that at the end, the prediction of one instrument, whatever the instrument, is the same. We do that, I told you, in mid-infrared. So this is the dispersion you can see for different mid-infrared instruments. And after standardization, we reduce. You can see that this is the variation we had at the beginning, one color, one instrument. And then you can see that we can gather all this variability in the green bullets here. And so we reduce a lot the dispersion. Doing that, we can have really high performance network, and we can get the possibility to reach high quality results. And what is important is that we can reduce highly the use of regions. So this is really a green technology. And doing that, using less region, we allow to keep also some effort to do other things, and we still need reference value. So we still need some kind of a reduced fraction, about 5 to 10% of the sample have to be analyzed by reference analysis, but we can manage more sample a day by one technician. So there is definitely advantage, and the method is the accuracy is the same, and the precision is a little bit larger than the reference method, but is totally acceptable for the food. Today, the application of vibrational spectroscopy will be in our institute a different kind. So I take just here 4 of the project we are running, just to telling you what we are doing with vibrational spectroscopy. So we bring the instrument, we go to the field in order to detect there is some disease in the field. For instance, this is the fenweed project, the first one. We are developing also a mobile app. The idea there is to bring this instrument and to make demonstration to the factories, for instance, just to telling them that there is new tools that they can apply, they can make benefit of this. We use also such a technique to detect fraud in pesticide. In this case, when I say in pesticide, is the raw pesticide, the raw material. There is also fraud, and then we try to be able at the border to control if all is okay. And last but least, we have also the Valserval project, and this is a project on wheat and barley. And there, the idea is to come with new tools where we can do allotment, we say in French. We can split, let's say, one batch in a fraction of top quality of wheat and another fraction, let's say, a lower quality that we will use for feed or for biofuels, for instance, but the top quality we will use, for instance, for food. And then this is the Val-Serval project, where we try there to improve the valorization of medium batch, I would say, the batches of medium quality. And there we have equipped our lab with different tools, very nice. I'm sorry because the slide is in French. I forget to translate it. But in the central part, what you have, it's very nice because we use the near-infrared in order to make single kernel splitting in one batch. So it means that we can start with, let's say 100 kilo, and then we can split this fraction on the single kernel batches using the infrared. So that's quite interesting for us. There is another where we use also infrared spectroscopy for on the feces. This is just to give you, if you want, you can go back to the slide and you can contact me if you want more information of this example. We use also for insect meal. You know, there is more and more production of insect meal for food and feed. Here it's more dedicated to feed. But what we try to do is to identify the species and the characteristic, and we use a vibrational spectroscopy for that. In the last time that I have known for the last slide, what I want to discuss with you very shortly, it's about NIR imaging. This is something that we have started years ago. And we use it firstly to detect animal protein. But I will not talk about this. What I want just to catch your attention is that when you have a mixture of particles, let's say in feed, this is what we have, you have a lot of particles, and with imaging, what we can do is to get spectra from individual particles. And doing that, we can go down in the detection of limit of the vibrational spectroscopy. If you look to classical vibrational spectroscopy, where we have one sample, one spectra, you can easily calibrate for different parameters that are the percent level. If you go with imaging, we can go down on the same sample, we can get 1,000 or more spectra by sample, and each individual spectra we can apply models, and then we can reach the ppm level of detection. I will show you this a little bit more. This slide explain you a little bit the difference between the benchtop and the imaging, and here we have a slide where you have the different application we have yet done. It's a summary and it's not all, but we can use to detect if, for instance, the cocoa beans are well fermented or not, to detect the presence of ergot particles in wheat, to detect the adulteration of species, of the presence of microplastics, and so on and so on. This is something that it's very exciting. It's no since we are working on this since 2 decades, but I would say this in 1 decade there is a lot of other team working, and we see definitely advantage for food analysis. Why? Because if you take one kernel, this is just the picture of one kernel, and you adapt the speed of the measurement, you can get from one kernel 250 spectra from one kernel. So it means that you doing that, you can do spatial study. You can study, for instance, the starch distribution or the fat distribution in one single kernel. That's something that's quite interesting for different study when you want to understand better your product. But what we can do also, you can go faster, and then you take 1 to 3 spectra by single kernel, single object, and then you say, okay, this object is wheat, for instance, in this case, or it's an adulterant. In this case, we try to detect a contaminant, it's ergot bodies. This is something that's happened in cereal production. In the flour moment, what can happen, there you have a spore, and then you have a fungi development, and then there is a body develop instead of the grain. And that's what we try to do. It's when you have the sample is to be able to detect in the sample the presence of ergot. And here what we have, you have in green, this is the belt where we put the sample. So this is the background. In blue, it is what is classified as wheat, and in red, it is what is classified as ergot bodies. And this is very interesting, and we have made the demonstration that we can go to the ppm or even lower with such a kind of technique. Because in 1 hour, you can analyze 40 kilo. And if you have 1 ppm adulteration of 40 kilo with ergot body, it means you have 1 of 2 ergot body in the 40 kilo. This we can do with that technique, we can analyze. We can do it in powder, that is demonstrate also. And what's very nice is when you get the information, when you have the spectra, you can apply a lot of different models if you wish. In our case, we can detect more than 30 different impurities of status of whatever of contaminant in cereals. So that's what we can do, just making one measurement, but applying different models. That's the thing. We cannot do all, but we can detect a lot of different things. And of course, when I speak detection of contaminant, it's particulate contaminant. We will not use this technique to detect dioxin, for instance, but for strange body impurities and so on, that's the right technique to use. And we have used this also with Barilla, for instance, because there they want to discriminate between the wheat that are the wheat, they use the durum wheat, and they do not want to have too much common wheat in the sample. And so what we can do, we can check the batches at the single kernel level. And that's quite interesting because so we can check that there is no more than 3% of kernel of a common wheat variety in the durum wheat variety. And that's important for pasta in order to get it. And what is very nice, when you have the imaging, you have the spatial information. So you can combine the spectroscopy information, single kernel, a single pixel, one spectra, and then you can do what you want. But at the same time, you can take information about the shape. And so in some extent, it helps to discriminate also there the size, for instance, of the kernel and so on. We did also this on a pea, for instance, but there we go to the root. And what we want to do there, it's to be able to detect on the root the presence of nodule. You know, the nodule, in fact, it includes a consortium of bacteria that will fix the aerial nitrogen. It means that then it's why pea are interesting. They fix the gaseous nitrogen, and then it make available to the plant. And we were able to go to determine the LEC hemoglobin. This is the enzyme responsible to the transformation. And then we can make study to know exactly what is the content on the single nodule when it is on the root. And that's for physical study, that's quite interesting. In order to finish my talk, few slides now about the cacao. I think it's a good thing to finish there. You will remind a little bit this presentation, I hope, that we speak about chocolate. We are Belgium. And we had a nice project with Brazil, where in fact, in Brazil, you know, the Amazonian basin, it's the origin of the cacao. And they have there a lot of different phenotype. And so they want to have tools that allow them to check rapidly the different phenotype present there. And so we had the chance there to look to this individual kernel. So what we did there, we have collect in the Amazon basin different varieties that the phenotype that they are using. And so that's quite nice because there they have the availability to use up to 20 different genotype. And what they do with this 20 genotype is that they mix them, they plant them all together. It makes that they will assure a more constant production, but at the meantime, they will assure also a more resistant to the different kind of illness. And so that's what we have done. We had the chance to have access to excellent material, very well referenced, and then we decide to work on it in order to be able to discriminate and to be able to check in a mixture of samples if we are able to detect the different phenotype. And for that, what we did, we collect the samples and then we use near-infrared hyperspectral imaging in order to be able to detect the different sample according to their phenotype. And here you have what we did. So we work in the strategy, we have analyzed all the sample, and then we have to build models. And to do that, we decide to build models from different way, but the idea is to be able to classify the model in the different class. So here we have an example of two classes. So we have the phenotype RMC and the P7. And then what we built a model in order to discriminate both of them. And then we make some tests. And what we use, we can use the individual pixel prediction, just to say, okay, this pixel from this bean is classified in class 1 or 2. But we can also work on majority vote. It means that you have one bean and you can say, okay, 90% of the spectra of this bean are classified from the class 2. And so you say, okay, the beans is from class 2. We have also a way where we can work on the mean and so on. So there is different ways, what the figure here present there. Of course, we did that in mixture, not only the slide before, we just present what we saw clearly on pure image, but we also in the same image, we put mixture because this is our purpose, just to see how different strategy to make the classification of product is working. And what is the aim at the end? Of course, it's not to analyze only an image, to have an automatic system that allows us to say, okay, at 90%, 95%, this is from this phenotype or not, or this is a mixture. And this is what we did. But in addition, and this is also very interesting, what we had, it's this other parameter, because when you do, you prepare cacao for the exportation, so cacao beans for the exportation, you have to make fermentation, it takes times, and then you have to dry. And this has to be done very, very strictly, in a stricter manner, because if not, you will have cacao beans of very bad flavor. And if you want to have top quality cacao beans, you need really to be very careful and to check this at the single kernel level. And so what we did here is at the same time we tried to look to different phenotype, we check if it was possible to say that the beans is well fermented and not. And so the idea there, it's both. It's a way to have a technique that at the production site, in South America, in Africa, and so on, we can check if the material we produce is top quality. And also in a European country to be able to check the raw material, but at the single kernel, the single beans in this case, level. It's very important because you know that when you have in one batch only few kernel, that the beans that are not very well fermented, it can damage the full batch. And so you have to check carefully. There is procedure to do that. It takes time. It is destructive, but here we succeed to develop models that allow us to say this is well fermented or not. And when it is well fermented, you develop aroma that you look for in chocolate. And so you can do fine chocolate. That is what we are looking mostly in Europe. So that's quite important for us. So that just to give you an overview of all what we can do with vibrational spectroscopy. So vibrational spectroscopy, it's a technique working with light, and we look to the interaction between the light and the matter, saying that the part of the light that is absorbed has the information on the product. I have to do some advice before to go to the conclusion. It's that definitely vibrational spectroscopy is very interesting. We can bring the lab to the sample, that's one for sure, but we have to be careful. You can do a lot of things, but you can do also wrong thing. And so what is very important is that you have to be sure and you have to be very robust in the time to validate. So when we develop models, for instance, the idea is not to produce the sample that you know, it's a product the week after, the month after, new sample to determine the parameter, a new sample. And so there in all the procedure, we have to be very strict, and we can help you in all the steps about validation. So that was just to give you a short overview. I make a selection. I'm sorry. I hope it fit what you expect. And here I want to thank, of course, all my team. Here you have the different people that work, because it's a lot of project, but you see there is a lot of people. And also just to make a short advice is that in October we have our annual vibrational spectroscopy and chemometry course in our institute. And so since more than 10 years we are organizing this, and we and that time the people can come. We speak about spectroscopy, we speak about chemometrics, but we play also with the data and with the instrument. And so you are welcome. And just to finish, just a funny slide that I just find. And I want to thank you. And now I'm ready for the session about the question and answer. Thank you.
Thank you very much, Vincent, for sharing your expertise in the field. And for everyone else watching, we will now move on to the Q&A session. So be sure to submit your questions now. I can see we have some questions already. So to kickstart the Q&A session, for your first question, what are the main applications of vibrational spectroscopy in food?
So can you hear me? It's okay?
Yes, I can hear you.
Okay. Okay. So the main application for the time being, I would say it is in feed, so alimentation for animals, okay, where it is used daily to assess the quality. And also I want to mention milk analysis, where there we use the mid-infrared daily in all over the world in order to assess the quality of milk and to pay also the farmer in terms of regarding the quality of the milk they produce. This is, I would say, the two biggest application. But in food and feed, you have also, for instance, in the meat industry, it's used a lot. It could be used also in the cheese industry, and so you have a lot of different application where the technique is used at the laboratory level, but could be used also at line, just near the process production, or also online.
Thank you, Vincent. For your next question, what are the challenges to implement a vibrational spectroscopy method?
This is a very good question. Usually, I say that a spectrometer is not an espresso machine, because it's not because you put a coffee in it that you will get a good coffee. And so that's the same with vibrational spectroscopy. There is a lot of very nice instrument, but you need to think in addition to the instrument. You need firstly to measure properly. So the way you will present the samples to the spectrometer is very important, because we are looking to the interaction between the light and the matter. So if you are wrong in that way, you will have a wrong spectra. And then all what you will do will be lost, because you will not be able to use properly. So there, all the procedure exists, all the manufacturers, know exactly how to measure, and so that this is a very important point. The second point is to have the good models. If you want to determine, let's say, from cereals the protein content, you should have a very good model that allow you to take the absorbances that you get, for instance, in near-infrared, and to make correlation, to make prediction of the protein content. And so the models, the mathematical models, are also very important. But there is a lot of solution. Some of the provider of instrument provide with the instrument with the different equation, the different models you need to determine the different parameter, and other not, but you can buy the instrument. And if you are in a very specific niche, we say in French, is a very specific domain where the application of vibrational spectroscopy is not so broad, you can build also yourself your model. But there it's more complicated, and there you have to be very to take a lot of to take care in order to be sure that the model you will develop will do the work, and the work is to predict, let's say, future samples.
Thank you so much, Vincent. Unfortunately, that's all we have time for. Any questions that we didn't have time to get to will be sent to the speaker after the event. While you're here, don't forget to check out all of the free-to-download literature and resources available below the live stream player. And as with all the other talks in the event, this talk will now be available to view whenever you want for the next 30 days.
Thank you so much, Vincent and Princess, for that wonderful wrap up to our final day. So that's it for this year's online symposium, Advances in Food and Beverage Testing. As mentioned throughout the day, all the talks from today's event will be made available to view on demand for the next 30 days. You can access the talks via the same link you used to access them today, and we'll be sure to pass on any further questions you submit through the system to the relevant speaker. That just leaves me to say thanks again, and we'll see you again at our next online symposium, The Modern Lab Leader. Goodbye.